Kia ora and welcome to Lecture 7 for 161324 Data Mining. So for the next 3 weeks we're going to be looking at classification. And so classification is basically the same idea as prediction, except our variable of interest, the outcome or target variable, is going to be a class variable. So it's going to be a grouping variable, right? So the goal is to assign each observation in the test set to one of a small number, or a finite number at least, of pre-specified categories. And the idea is we're going to do basically the same thing as we did for prediction, where we have a training data set for which we know the classes. So we know both the class and some predictor information or feature information. And then we're going to use that to train up a bunch of models, and we're then going to use those models to predict the class for new data. So it's sometimes referred to as being as supervised learning, in contrast to unsupervised learning, which is clustering, which we'll do in week 10. And there are a huge number of applications for this. Just some are listed here. Obviously, there's things like diagnoses of disease, right, where your interest is whether the person likely has a disease or not, and your predictors are then some perhaps some tests. There might be an MRI or a biopsy or some genetic markers and whatnot. And your goal is to use those features, the genetic markers, the results from the MRI or image scan or something, to decide whether that person is likely to have disease or not. Now, usually we can't expect to get things perfectly right. And so we need a measure to decide which class is likely is the most likely given the predictive variables that we have. So an observation with a given set of values for a predictor or a set of predictors could potentially belong to multiple classes. However, generally, one class will be more likely than the others for any particular observation. So a simple example is that suppose you want to decide to determine if a video on Netflix is from a TV series or a movie, right? And one of the predictors that you have is its length, right? So how long is the particular video file? And if the video is close to a couple of hours long, then it's likely to be a movie, right? Because movies are typically a couple of hours long, whereas TV episodes are typically shorter, but it's not perfect, right? So some TV episodes are longer and some movies are shorter. So there's some uncertainty there, but nonetheless we can use the fact that typically movies are longer than TV show episodes in order to assign on the balance of probabilities. So to do that, we need to estimate classification probabilities, which is the probability of each class. So that's each level of the target variable, given the features that we have observed. So given the predictors, right? So it's the probability of the target given the predictors. And we typically assign to the class that has the highest classification probability. Okay. In some cases, we may not want to assign directly to the class with the highest probability, because there may be a cost involved in assigning things incorrectly. So for example, in medical diagnoses is a classic one, often things depend on other knowledge that you have about the patient over and above the particular set of predictor variables that you're using to make a diagnosis. Okay, so for example, if you have a very rare disease, then you know that it's extremely uncommon. And so if you have a test for that rare disease, then that test is going to have some false positive rate and some false negative rate. And if it's extremely rare, then the false positives can, in some cases, overwhelm the true positives, right? So a simple case is, say your false positive rate is, say, 90%. So your false positive rate is only 10%, which is quite high, but let's just go with it, just an example. And then say that the disease is very rare, so it only happens, say, 1% of the time, right? So if you tested everyone, 1% of the time those people actually have the disease, and let's say the test is perfect then and returns a positive, right? So if you tested 100 people, then 1% of them, which is 1, has the disease and you detect it, right? But the other 99 don't have the disease, but the test isn't completely perfect in terms of the false positives, and so 10% of those 99 are going to test positive incorrectly, which is about 10, right? So 10% of 99 is about 10. So all up, you're going to have about 11 positives, but only one of them is a true positive. The other 10 are false positives. So in that situation, you wouldn't necessarily go purely based on the classification probability. You'd also want to take into account how rare the disease is and what other information you have about the person. So there are two main approaches to classification, different classification models, and they are generative classifiers, which is what we're looking at today, which have some statistical and some mathematical theory behind them using Bayes' theorem. And then there's discriminative classifiers, which we'll look at next week, which are sometimes known as conditional classifiers. And generative classifiers generate those class probabilities by first estimating other things. Okay, so we're generating the probability of a class given the predictors by estimating a bunch of other things first. Typically, we estimate the probability of the predictors given the class, so the conditional probability the other way around. Whereas discriminative classifiers, we estimate those probabilities directly, and we'll see how to do that later on. So a little bit of statistical theory for generative classifiers. Let's set up some notation. So we're going to have C possible classes, so 1, 2, 3, 4 up to C, whatever C may be. Okay, and we're going to have a vector of features or predictor variables, and there's going to be P of them. Okay, so those are our information that we're going to be observing on both the training and test set, and the labels are only going to be on the training set. And then we're going to denote F sub j as the joint probability function of x for individuals in a particular class j, right? So we're going to have an F1 for the first class, which denotes the distribution of these x1 through xp's, the joint distribution, within that class. And that distribution is likely to differ from class to class. If it didn't differ, then we wouldn't be able to distinguish the classes. So we're assuming that fj is going to differ from class to class. So the probability function fj defines the conditional probability of the features for any given class, right? So it's the probability of a probability distribution of the x's for each class. So given the class, what do the x's look like in terms of how they're distributed, right? So for example, in the case of the Netflix, then given the class's movies, we would expect the length of the movie to be perhaps, maybe it's going to be normally distributed or something if we're lucky, centered on, say, 2 hours, right? So that would be the probability distribution of the length. Whereas perhaps for a TV show, then maybe it's going to be some sort of bimodal distribution, centered on with the two modes centered on, say, 22 minutes and 45 minutes, which was sort of the classic lengths for a 30-minute and 60-minute TV show back when TV was aired over the air and had adverts and whatnot. I guess it still has adverts, doesn't it, really? But those lengths are often still maintained, although slowly we're diverging from that with streaming services. So those distributions differ, and we're going to be using the information in the difference between those distributions in order to figure out, given a particular length of a video file, is it likely to be in the first class, the movies, or the second class, the TV shows. And the other piece of information that we need is called the prior probability of each class. And so that's what's the probability of an observation drawn at random being a movie if you didn't know the length, right? So you don't know anything about this video file. What's the probability of it being a movie? What's the probability of it being a TV show? And you could just use frequency information for that. So for example, there's perhaps many more TV show episodes than there are movies. I don't know actually if that's true, but let's say it is, right? So if there are many more TV show episodes than there are movies, then if you didn't know anything at all about a target observation coming in, then you might think that it's more likely to be a TV show than a movie just because there's more TV shows, right? So that's your prior probability for each class. And so there's one for each class, obviously, and they will sum to 1. So let's have a look at a very silly example. So we have a renowned entomologist, Professor Hamish McTwaddle, has a collection of 1,000 bellbugs and frongles. So these are insects, and each insect is either blue or green and either has 1 stripe or 2. So there's 4 different possibilities. You have a blue 1 stripe, a blue 2 stripe, a green 1 stripe, or a green 2 stripe. And each of those insects can either be a bellbug or a frongle. Then let's figure out what all these probabilities are going to correspond to. So the prior probability is the probability of being a bellbug when you haven't seen the insect, right? So you don't know whether it's a blue 1 stripe, a blue 2 stripe, a green 1 stripe, or a green 2 stripe. And so we could just use frequency for that. So we could just use how many bellbugs do we have, how many frongles do we have, right? So we know we've got 1,000 total. And if we add up the number of bellbugs going along the row here, we've got 50 plus 20 plus 230, that's 300, plus 300 is 600. So we've got 600 bellbugs, and we've got 1,000 total. So, and we've got 400 frongles and 1,000 total, right? So if you hadn't observed the insect, you just hear it burrowing around, you'd be more likely to say that it's a bellbug than a frongle just because we've seen more bellbugs, right? So the prior probability of being a bellbug is 600 out of the total, 1,000, 0.6. Probability of being the frongle is going to be 1 minus the probability of being the bellbug, so that's 0.4. Or we could work it out directly from the table, 400 over 1,000. Okay, what about these F1 and F2, which is the distribution of the predictors? Remember, the predictors are whether it has are these things along the top here, so whether it has 1 stripe or 2 stripes, and whether it's blue or green. There's 4 combinations of the predictors. So what are the probabilities of those given we know the class, right? So this first one, F1, class 1 was bellbugs. So this is the distribution of blue 1 stripe. So the probability of observing a blue 1 stripe given that it's a bellbug, right? So we're ignoring the frongles, we're just looking at the bellbugs. And so that F1 is the probability of it being a blue 1 stripe if it's a bellbug. So we know that there's 600 bellbugs, so we're only looking at the bellbugs. So we're only looking at this row here. So we know there's 600 in total. And how many of them have blue 1 stripe? There's 50. So the probability of it being a blue 1 stripe is going to be 50 out of 600, right? Which is this number here. Similarly, the probability of it being a blue 1 stripe, if it's a frongle, there's 200 of them. So half of the frongles are blue 1 stripes. Right, so you get a much higher probability of being a blue 1 stripe if you're a frongle compared to whether you're a bellbug. So you might think, looking at these two numbers, that if you saw a blue 1 stripe, it's more likely to be a frongle, right? Because this number here is way bigger than this number here. And that's correct, but only after we take into account the prior probability of observing a frongle or a bellbug. And the reason for that is, suppose we'd only seen 5 frongles, right? Oh, well, maybe, let's say 10 so that the numbers work out better. So say we'd only observed 10 frongles, right? And we'd observed 990 bellbugs. Then bellbugs are way more common than frongles. So even though blue 1 stripe frongles make up half of the frongles, and blue 1 stripe bellbugs only make up a small percentage of the bellbugs, because there's so many bellbugs, that small percentage is going to overwhelm the large percentage of the very small number of frongles. Right? So we can't use these probabilities directly. We have to account for the prior probability. Okay, and just another example. What's the probability of being a green 2 stripe if you're a frongle? We're doing F1. Remember, if you're a bellbug, group 1 was bellbugs. So again, we're looking at green 2 stripes. There's 300 of them out of 600, so that's 0.5, and there's only 30 out of 400 for the frongles. So again, looking at these two numbers, if you saw a green 2 stripe, you might suspect it's a bellbug over and above the Frongal. But again, you have to take into account the frequency information. Okay, so in order to do classification, given the green 2 stripe or the blue 1 stripe, we need to combine these numbers here, F1 and F2, with the pi's, right? And we do that using Bayes' theorem. So the classification probability for class J, given the feature vector X, is the conditional probability of being in class J given X, right? Which is which is the other way round to the conditional probability Fj, right? So Fj was the probability of X given J. Here we have the probability of J given X, so we need to switch that conditional probability around, and that's what Bayes' theorem does. So this thing here is known as the posterior probability for class J based on data X. And the goal is to figure out what this is, given that we know what Fj and pi j is. And we can do this using Bayes' theorem, which is this formula here. Right? So this is something that you should be intimately familiar with for the rest of the course. And we'll see how it's derived on the next page, on the next slide. But you can see here that to work out the probability of J given X, what we have to do is we have to take into account the prior probability of being in that class, as well as the probability of observing the vector X on that class. Right? So we're combining, if you like, pi 1, the probability of a bell bug, with F1, the probability of, say, a green 2 stripe, given that they're a bell bug. So we're combining those two things together. And then we have to divide by the total probability of observing X, okay, which is just the sum of the numerators here over all the classes, right? And that makes sense because, of course, these probabilities of each class J have to add up to 1, right, if you sum over the classes, because an observation has to be in one of the classes, right? So the total probability is going to be 1. So the denominator equation is the same for all classes, so you only have to work that out once. Okay, so if you're doing this by hand, you have to work out what these products are. Okay, then you add up all the products, and that's what the denominator is, and then it's just one over the other, right? And the most probable class is then the one for which the numerator is largest, because the denominator is always the same. Okay, so you can do the assignment of an observation to a class without having to work out do the summation. Okay, that's important in other applications other than classification, right? Doing the sum is actually a trivial thing to do. So where does Bayes' theorem come from? Well, it's been around for a long time. It's attributed to Reverend Thomas Bayes, who's this fella here, but it was developed in parallel by others. And it's really the foundation of one of the largest branches, one of the sort of most important branches of modern statistics, which is Bayesian statistics. And it's all based on Bayes' theorem. And this is how Bayes' theorem works, right? So it's just a way of reversing conditional probabilities. So say we want the probability of A given that we've observed B. Then using the formula, using the definition of conditional probability, that's just the probability of observing both A and B divided by the probability of B. That's the definition of conditional probability. And then we note that we can reverse the order of B and A in the AND statement above, right? Because that's symmetric, the order doesn't matter. And then we can again use the formula for conditional probability to write this as the probability of B given A times PA, right? And so now we've taken the conditional probability of A given B and we've written it in terms of the conditional probability of B given A. And to do so, we've had to take this extra ratio, PA over PB. Okay? This is sometimes known as the Bayes factor. Okay. So, let's do it with our bell bugs, right? So, the probability that a blue one stripe is a bell bug, right, is given by the probability of a bell bug given that it's a blue one stripe. And so we can just chuck that straight into Bayes' theorem. We've worked out pi 1 f1, right? So pi 1 would be the probability of a bell bug, which is just 600 over 1,000. That's easy, so that's 0.6. F1 is going to be, F1 blue, one stripe is going to be 50 out of 600. So again, that's 0.083. So the numerator is 0.6 times 0.083, and then that features down in the denominator as well as the opposite term. So pi 2 is going to be the probability of a frongal, which is 400 out of 1,000, that's 0.4, and the probability of a blue one stripe, given that you're a frongal, is 200 out of 400, so that's 0.5, and so if you do the arithmetic, you've got 0.05 divided by 0.05 plus 0.2, and so you get the answer 0.2. Right, so if we see an insect and it's a blue one stripe, then it's a 20% probability of being a bell bug and a 80% probability of being a frongal. Right, so that's how we turn those probabilities around. Now this can actually be done a lot easier without having to work these out, right? You can do it with fractions a lot quicker, right? So this fraction here is just 600 over 1,000, and then this one here is 50 out of 600. So you've got 600 out of 1,000 times 50 out of 1,000. It's just 50 divided by 1,000. And similar things happen here, and so you can cancel out the division by 1,000, and everything drops down nicely. You just get 50 over 50 plus 200. Okay, and everything works really nicely. So if you've got a table, you can actually work it out by hand relatively quickly. What about if you're a green two-stripe? What's the probability that you're a frongal? Then it's going to be the prior probability that you're a frongal, which is 0.4, times the probability that you're a green two-stripe, given that you're a frongal. Green two-stripe is 30 out of 400, so that's 0.075. So that again is going to appear down the denominator. And then we also need the probability that we're a bell bug, which is 0.6, 600 out of 1,000. And the probability that we're a green two-stripe, given that we're a bell bug, is 300 out of 600. So that's 0.5. And if you do the arithmetic, you get 0.09. Okay, so there's a 9% probability that if you observe a green two-stripe, that it's a frongal. So that means there's a 91% chance that that thing would be a bell bug. So if we're observing a green two-stripe, we're sort of 10 times more likely to be a bell bug than a frongal. If we're observing a blue one stripe, then we're 5 times more likely to be or 4 times more likely to be a frongal than a bell bug. Right? Okay, so that's how we do classification using Bayes' theorem. How do we evaluate how well we do? Well, we can measure the misclassification rate. So the misclassification rate is just the proportion of observations in the training set or in a validation set, which would be a smarter thing to do, that's been assigned the wrong class, right? So we do the usual thing where we take our training data, we'd split it into an actual training set and a validation set so that we have an independent set for which we know the answer. We then train our model on the training set, we predict the class of the validation set, and then we have the predicted class and the true class. And then all we do is we cross-tabulate the predicted classes versus the actual classes, which gives us what's called the confusion matrix. So that's just the number of observations that are predicted in class 1, that are actually in class 1, the number that are in class 1 that are actually in class 2, and so on. And then we choose the classifier with the smallest classification rate, misclassification rate, or the highest classification rate. Sometimes we weight things. So, for example, false negatives might be more important than false positives if your outcome is a binary thing. For example, maybe in forensics, we'll look at an example of forged banknotes. If you've got a test for banknotes being fake or not, then you probably want to err on the side of letting through a few false positives. So you're saying a few banknote, you don't really mind if you say that a few notes that are actually fake are genuine, because you don't want to accuse everyone of being fraudulent in a bank, right? There's going to be some assumption that most of your customers are not fraudulent. So the note is going to have to be quite different before you start accusing someone of having a counterfeit note. Okay, so to design generative classifiers, we need to figure out what these pi's and f's are. Then we just plug it into the formula and we're done. Okay, so the question then is, how do we obtain prior probabilities and probability functions from training data? So we've seen how to do it in the simple case where our predictors are categorical and we can just draw a table up and work these things out directly. But what if our predictors are numeric? Okay, so here's an example. We've got this data on Swiss banknotes. Okay, and we can see that we have two pieces of information. We have the margin and we have the diagonal. So this is measured in, both are measured in millimeters. And so this is the diagonal across the print, I think it is. And this is the margin around the printed portion of the note. And then we have whether the note is actually forged or genuine. And the idea is that the forged notes may differ in some way in terms of their margin and diagonal compared to the genuine notes. So this is what it looks like if we just have a look at one of those variables, the margin. Then we can see that there's an obvious difference between the genuine notes and the forged notes, in that the genuine notes typically have a smaller margin than the forged notes. Okay, so if you measured the margin of a note that you don't know whether it's genuine or forged, and you got, say, 8 millimeters, then that's right at the edge of the forged distribution. So potentially it could be forged, but it's an extreme forged note, but it's a typical genuine note. So you would be more likely to assign it to be genuine than forged, right? Similarly, if your margin was, say, 11 millimeters, then that's outside what we've seen for genuine notes, whereas it's typical for forged notes. So that note would typically be assigned as forged. Okay. So there's a couple of ways we can do this. We could assign a distribution to this thing, or we could use information about the shape of the data in order, so a histogram, for example, in order to determine the distribution F1 and F2, right? So this is F1 and this is F2 from the data that we've observed. It's a box plot of that distribution. We could use a histogram, we could use a density, we could fit a normal distribution to it, and various other things. So for our prior probability, so that's how we do our distribution probabilities, F1 and F2, would be fit a distribution to the data that we observe. What about the prior probabilities? Then typically we would estimate them in the same way that we did for bell bugs and frongles. We just use the relative frequency. So how often do we see forged notes and genuine notes? Okay. Now that would be a bad idea that might be a good idea in the insect example, assuming that Professor McTwaddle collects insects at random in their natural habitat, so that you have a good sense of how common a bell bug and frongle are. But it's a very bad idea in our example, because in our example we have I don't know how many we have. So our training data has 120 records. I don't know if we say how many we have. I think it's half. Yeah, so it's about half and half, right? And so in our training data, it's about half and half. But of course, in real life, it's extremely unlikely that forged notes and genuine notes are equally common, right? It's much more likely that genuine notes are way more common than forged notes. Otherwise, we'd have a serious problem, right? We go to a lot of trouble to make sure that it's hard to forge a banknote. Therefore, the prevalence of forged banknotes is going to be really low. Okay. So in order to get these prior probabilities, we might want to ask experts as to the frequency of observing forged notes in practice compared to the total number of notes in circulation. So that's how we estimate. The prior to estimate the the F's, which is the conditional probability of the features given the class, then we can do a number of different things. And each of the different ways that we estimate these things gives rise to a different model. So the first model we're going to look at is linear discriminant analysis, where we assume that the FJs are normal probability densities. Then we'll look at kernel density estimation, which gives rise to kernel discriminant analysis, which is a sort of a more generalized form of linear discriminant analysis. And then we'll look at naive Bayes. Now these first two only work for continuous predictors, okay, whereas naive Bayes will work for continuous predictors and categorical predictors. Other models that we'll be looking at will deal with other categorical predictors as well. Okay, so we'll start with linear discriminant analysis. So linear discriminant analysis makes the rather large assumption that the F distribution, so that's the distribution of the predictors given the class. So within one class, what does the box plot, if you like, or the histogram, or the distribution of the predictors we're going to assume is normally distributed. And in addition, we're going to assume that the variance within each class is the same. Okay, so that each distribution looks essentially the same, and all that's happened is that they've been shifted around in terms of their center. Okay, so the classes are differentiated by the location of their means. So this might make sense in this case because the spreads here are roughly the same. I mean, maybe the forge is a bit bigger than genuine, but it's probably not too much that assumption is bad. And you can see that they're relatively symmetric, so using normal distributions for this data set is probably going to work quite well. Okay. So we'll go through the maths so that you can get a sense of how it works, and then I'll also view this graphically. So suppose we have the really simple case where we just have one feature in two classes. So this is the Swiss banknotes just looking at the margin, right? And we're assuming that each of the distribution of the margin within the genuine and forged notes are going to be normally distributed and have the same variance. Okay, so we could, based on the training data, we could estimate the common variance between the, so basically ignore the, whether it's genuine and forged, and use all the data to estimate the variance, taking into account the fact that each group is going to have a different mean, and we're going to estimate the mean in class 1 and the mean in class 2. So this will be the mean for the forged notes and the mean for the genuine notes, for example. Right, so our model, our LDA model, is going to be that F1 is a normal distribution centered on the mean of the forged notes, and F2 is a normal distribution centered on the mean of the genuine notes, and they both have the same spread. And we're going to also assume, which is silly in this case, in the case of the Swiss bank notes, that the priors are equal, right? So that we don't essentially have to account for them. So if we have a new banknote that we've seen, how should we classify it? So we have a feature value of x0, so that would be our margin. So from Bayes' theorem, all we do is we plug it into our formula, and we can work out these classes using, we can work out these probabilities using Bayes' theorem. And so we're going to assign it to class 1 if this thing is larger for class 1 than class 2. Right? And so we're assigning it to class 1 if the numerator is larger for class 1 than class 2. And because pi 1 and pi 2 are the same, they're both 0.5, right? We can get rid of them because they're the same, and so we're going to assign it to class 1 if the probability of observing the particular margin in class 1 is higher than the probability of observing that same margin in class 2. So we have normal distribution, so we could actually go through the maths if we want to. Okay. So let's go through it painfully, if you like, to see sort of how it works. This is not something that you'll be expected to be able to reproduce, so feel free to skip ahead a couple of minutes if you wish. So the formula for the normal distribution of a single variable is this here. We have this 1 on root 2 pi sigma. x minus the mu squared over 2 sigma squared exponentiated. Then if f1 of x0 is to be bigger than f2 of x0, then we can just plug in what we know about f1 and f2 into these. So they're the same formula. The sigma is the sample standard deviation that we've got from the training data. That's the same for both sets, and the only thing that differs is the mean, right? And so you can see that this first term here is the same, and so we can cancel it out, and so we just have this expression here. And then if we take logs, then because the log function is increasing, it doesn't change the direction of the greater than sign, and so we just the only way that e to the power of something is greater than e to the power of something is if something is greater than something. So this is like e to the a greater than e to the b. The only way that happens is if a is bigger than b, and so we can just get down to there. And then s is the same, we can get rid of it. We can get rid of the multiplication by a negative by just reversing the direction of that inequality, and so we get this expression here. And the only way, then we can take the square root, and then we get this expression here. Okay, so when we take the square root, we've just got to remember that this thing here could be either negative or positive, right? Because when it's squared, it becomes positive, right? So we're going to have the absolute value of x0 minus x1 bar has to be smaller than the absolute value of x0 minus x2 bar. And so this here is just the distance of x0 from the mean. x0 from the mean. That's all it is. So we're going to assign it to class 1 if the distance from the observed margin to the mean of the forged notes is less than the distance of the observed margin to the mean of the genuine notes. Right? So if it's closer to the center of the genuine notes, it's going to be genuine, and if it's closer to the center of the forged notes, it's going to be forged. And that's very natural, right? Now the maths maybe isn't very natural, right? But the idea is very natural. So we're going to assign to class 1 if the distance from the observed predictors to the center of the distribution is smaller than the distance for the other class. So here's a more natural way to look at it, right? Let's just plot what these distributions are going to look like, right? So we've got two normal distributions, right? And I've just arbitrarily said that the group 1 is less than group 2, but we could swap them over, right? We could just relabel this as mu2 and this as mu1, the same idea applies. Then you can see that if basically where they cross over is where your decision boundary is, right? So if we're to the left of the dashed line there, which is where they cross over, which is halfway between mu1 and mu2, right? It's the average of those two, if you like. If we're on this side, then the blue curve's higher than the red, right? So that means that f1 is higher than f2. Okay, so we're going to assign it to class 1. And if we're on this side, then the red curve's higher than the blue, and we're going to assign it to class 2. And that makes sense in terms of like where the centers are, right? So as long as you're closer to the center mu1, right, so you're to the left of that dashed line there, you're going to be in class 1. And if you're to the right of that dashed line, you're closer to the second mean, you're going to be in that group. And the maths just basically tells us that this happens, right, in sort of a formal way. But the idea is very intuitive. Right, so we're going to assign to a class if it's the closest class, basically. Okay, and the same idea extends to more classes and more feature variables. So the maths is basically the same. I mean, you know, there's more variables involved, but the analysis works exactly the same. The equivalence of like a boundary here applies, but your boundary is now basically what's called a linear separator or a hyperplane. So here's some pictures of what happens when we've got two predictors and two classes on the left here. All right, so we've got a predictor x1 and a predictor x2, and there's the center of x1 and x2 is centered at 0, 0 within class 1, whereas it's centered at 1, 1 within class 2. Okay, and so essentially all we do is we draw a sort of a line between mu1 and mu2 and we bisect it. And then if you're in the grey zone, you're closer to mu1, and if you're in the blue zone, you're closer to mu2. Okay, if you have 3 classes, the same idea applies, right? It's just there's more lines dividing the group. So if you're closer to mu3, then you must be closer to mu3 compared to mu1, right? So there's a line through here, to the left of that, and you must also be closer to mu3 than you are to mu2. So there's a line through here, and so that's the area for mu3, and then that's the area for mu1, and that's the area for mu2. Okay. So basically, all you do is you say, how far am I from each of the centres? Whichever's the smallest, that's the group I'm going to be with. That's if the priors are all the same. If the priors aren't the same, then we just shift that hyperplane, shift that decision rule, if you like, right? So the left case is the case we had before, where mu1 was at 0, 0, and mu2 was at 1, 1, and there was that nice 45-degree line. And then if you were closer to mu2, then you're in the second class. And if you're closer to mu1, you're in the first class. If the priors change, so here we've said that the prior for class 1 is 2/3, and the prior for class 2 is 1/3. So class 1 is 2 times more likely than class 2. All we do is we move that decision barrier towards mu2, which makes the area around mu1 bigger, right? So now, as long as you're in this grey zone, which is now bigger than what it was before, you're assigned to class 1, because we know that before we knew what the predictors were, before we knew what x1 and x2 were, we were twice as likely to be in group 1 anyway, right? So that knowledge basically extends or expands the probability of being in the first class and shrinks the probability of being in the second class, which is natural. So for example, in the banknotes situation, right, we know that the probability of being a forged note before we've looked at the note is actually really small, right? So that's going to shrink the posterior probability of being a forged note. So essentially what it's going to do is, back in our case where we had these, let's have a look at here. So instead of sort of having a dividing line just through here and assigning to genuine if it's say below, say 9.5, and assigning to forged if it's above 9.5, what we're going to do is, because we know that forged notes are really rare, is we're going to shift that line up, right? And so we're going to make it say maybe at 10.5, right? And so what that's going to do is it's going to mean that a bunch of forged notes are going to be incorrectly assigned genuine, but we know that forged notes are super rare anyway, right? So there's only a few of them. And so if we get a half of a few wrong, that's a small proportion of wrong compared to the genuine notes, of which there's overwhelming numbers, and we're going to get almost all of them right. So overall, we'll do way better. Okay, so in R, we do this using the LDA function, is the underlying tool. It's in the mass package. And in practice, we're going to use the discrim linear wrapper function, which is going to be a tidy models function. So it's in Parsnip in the add-on package discrim. So you'll need to install the discrim package, and then you'll use discrim linear in our tidy models setup. If we want to define the prior probabilities, then we can set the prior argument in set engine. By default, it will use the proportions in the data, which is often what we might want to do, but not always. And then classifications are then done using predict or augment in the same way that predictions are done. And then we can use the conf mat function, which is short for confusion matrix, from yardstick to evaluate performance. And there's also things like accuracy, which gives us our classification rates. So let's have a look at an example. Okay, so we load the library discrim and the library yardstick. Okay, and then we set up our model. We're going to have a linear discriminant analysis, and we're going to fit type in terms of all of the other variables, which are going to be margin and diagonal, using our training data, and then we're going to have a look at the outcome. And so we have a parsnip model, and then the underlying LDA object, you can see that it's estimated the priors from the data. So it's saying that there's a slightly higher chance of being forged than genuine, just because we have more forged notes than genuine in the training data. So this is obviously going to be a silly thing to do for predicting new notes, but maybe it's okay on our training data and on our validation data as well. But we probably want to alter these in practice. And then what it's done is it's estimated the mean of the margin and diagonal within each group. Okay, so you can see that the margin in the forged group is 10.6 and the margin in the genuine group is 8.4. That's what we saw in our box plot before. And it's also done that for the diagonal. So you can see that genuine notes tend to have a smaller margin and a larger diagonal, whereas forged notes tend to have a smaller diagonal and larger margin. And then it's also identified the coefficients of the linear discriminants, which is basically a matrix transformation from the scaled margin and diagonal to the formulas for those hyperplanes that divide the observations up. We could do prediction in the same way. So for example, we've got our Swiss test set, artificial test set that has the correct answer. And so we can use augment to do that. And by default, it will add a predicted class column. So this is the prediction of each of the rows in the test set. So the first observation is forged, the second observation it thinks is genuine, and so on. The type over here is the real observation. So you can see that we're getting things right actually pretty well. Row 10 is incorrect. Okay, it's actually genuine and we've predicted it to be forged. It also gives two other columns, which is the probability that it's forged and the probability that it's genuine. So these are the posterior probabilities from Bayes' theorem. So they add to 1. You can see that it's really confident, right? So it's basically it's 1. The probability that it's forged is 1, and very, very tiny probability that it's genuine. And it's reversed for the second one, right? Almost close to 1 here and almost 0 here, and so on. You can see that when it gets it wrong, it's super confident, right? So it's saying it's 98% chance of being forged, but that was actually genuine. Okay. And then the conf-mat, you supply the truth, which is the column from your data that is the true answer, and your estimate from your which will be your .pred class column, and then it just tables them up. And you can see that out of the 36 forged notes, it got every single one of them correct. And out of the 44 genuine notes, it got 43 of them right and 1 wrong. So we've done extremely well on this problem. But of course, this is an extremely easy problem for LDA because the data separates super well. And the distributions of the diagonal and margin within each group are very close to being normally distributed. We can see that when we plot the data. Okay, so here's the plot of the data. I've plotted both the training data and the test data. So the training data is the light colored points, and the test data is the dark points, and then it's colored based on the true type. And so you can see here that, that it you could estimate these two things using normal distribution with the same variance. Okay, maybe this one has more variation than this one, but it wouldn't be a huge, wouldn't be massively incorrect to define these using the same covariance matrix. And you can see that they're roughly normal, so they're shaped kind of like ellipses. And so here's the linear discriminant. And so you can see here that we're only getting one of them wrong, which is this one here, right? So everything on this line is going to be red, everything on this line is going to be blue. So in the training data, we're getting this one wrong. In the test data, we're getting this one wrong. It's unclear whether we're getting that one right. I think that one's getting it right, okay? But there's a couple that are very close to the boundary here. So the key thing to note here is that the LDA makes strong assumptions. So that normality assumption is very strong. But if it holds, it's going to do really well, right? But if it doesn't hold, it's going to do really badly. Okay, so here's a set of example data where we have a jam and a donut. Now, typically a jam donut doesn't really look like this if this is a donut with a hole in it, but you can imagine this is basically a donut with jam being injected into it, and then we've taken a cross section, right? And so perhaps it looks something like this, right? So we have two classes here, but you can see that the distribution of these things is far from normal. So maybe it's normal for the jam, right? It looks roughly like an ellipse, but it's definitely not normal for the donut, right? And the other thing is that the means of these two things are essentially the same, right? The centers of these two distributions are right in the middle here. And so we would expect LDA to do really poorly because the normality assumption doesn't hold, and in particular, there's no difference between the group means. And the group mean differences is the only thing that LDA can use to differentiate the groups. Okay, so sure enough, when we look at the confusion matrix on the training data, so this is home ground advantage, right? So we would expect it to do better than it would on, in practice on independent test data. You can see that it basically has no idea, right? So of the roughly 4,000 donuts, in fact, exactly 4,000 donuts, just over 2,000 of them it got right, and almost 2,000 of them it got wrong. And of the 4,000 jam observations, just over 2,000 it got right, and almost 2,000 it got wrong. So it's essentially tossing a coin, right? It's doing very slightly better than tossing a coin, but only very slightly better, and that's with home ground advantage. Okay, so LDA does extremely poorly if those strong assumptions don't hold. Okay, and in simple cases where you only have a few predictors, you can evaluate those assumptions by plotting the data. A little bit trickier in high dimensional cases, but you can do one variable versus another, or perhaps three variables at once or something, in order to get a sense for whether LDA might be applicable. So what if we drop that strong assumption? Then another thing we can do is use kernel discriminant analysis. So kernel discriminant analysis estimates the Fs using a kernel density estimate on the training data. And so a kernel density estimate, you remember we looked at those when we did geom density and ggplot. It uses this formula here, so this is the maths if you like, where essentially what you do is you have a kernel which is centered on each observation, so xi's here are the observation, and has some spread h, so the h here is the amount of spread of the kernel, and then you average them. So you can see here that this is an averaging process, isn't it? We add them all up and divide by how many we have. So it's just the average of a bunch of kernels that are centered on the observations. Okay, so h is the bandwidth. This is one dimension, but we can extend it to multiple dimensions, whereby h becomes a bandwidth matrix. So you have smoothing in the x, smoothing in the y, and smoothing in the combination of x and y. Okay, so we estimate this directly from the training data, and then we just plug it into Bayes' theorem. So that'll give us basically, so this gives us a formula for x, right? So xi's are known, h is estimated, so that's known, then we just plug x into this formula and work out that average. And then again we assign to the test class for which the posterior probability via Bayes' theorem is highest, just like for LDA. So recall that what a kernel density estimate is doing is it's essentially dropping a little, often a normal distribution on each data point and just accumulating them all in order to estimate what the actual shape of the data are, right? And so that allows us to be much more flexible than just a normal distribution. So you can see here that our data is basically bimodal, and we can then estimate that distribution more in a way that minimizes bias. And so on the jam donut case, then our distributions are going to be really good, because we're going to easily get the distribution in the middle. That's normal. Okay, that's going to be estimated well with just basically a single blob, right? The jelly's just going to accumulate, and then around the edge here, your blobs of donut, if you like, are going to accumulate into a donut shape. So it's going to do extremely well. This is the evaluation on the training data, so home ground advantage, but you can see that it gets almost all the donuts right and it gets all the jam right. Okay, so it only says that 2 donut observations are jam. So to do this, we use the discrim, in practice, we do use the discrim kernel function from the tidy KDA package. So this is a package that I've written to basically make the KDA function from the KS library usable within the tidy models framework. Now, I haven't actually submitted this to CRAN yet because I've still got to do more work on it and, time. So you can install it via the remotes install GitHub command. So you'll need the remotes package to do this. It doesn't need to build anything. So you don't need RTools or anything like that on your computer. You should just be able to run it directly in RStudio. If you have problems doing this, let me know, because I may be able to build it for you. I'm not completely sure. Now, it can be quite slow to run for large data sets, and the discrim kernel function only allows at most 3 numeric predictors. So if you have more than 3, then this thing won't work. Okay. Let's have a look at, I'll explain why in a moment. Let's have a look at KDA for the Swiss banknotes data. Okay, so as expected, it does really well because this is just a trivially easy problem to solve. So you can see here's our kernel density estimates in 2 dimensions. All right, so this one's centered here. That's the highest blob. This one's centered here. But you can see that it's doing something that's not purely symmetric, right? So this one has a bit more spread than this one and so on. But again, it does really well because this is easy. This is an easy problem to classify. Now, the problem with KDE is that essentially you're working out a huge number of parameters. So KDA works really well when the number of features is small. And in that case, it's going to work better than LDA almost all the time because it doesn't make the strong modeling assumptions that LDA does. And the LDA assumption will almost certainly not hold, right? Nothing is ever perfectly normal. But for high dimension number of predictors, and we're not talking very high at all, so more than about 3, then you get problems because of the curse of dimensionality. And the reason is that as the number of dimensions, the number of predictors increases, we need exponentially more data to give reliable kernel density estimates. And it's a little bit unintuitive, but one way to look at it is to consider things like, instead of a kernel density estimate, consider a histogram. Okay, so suppose you have a histogram for just one predictor, right? Then you might use, say, 10 bins, so 10 bars in the histogram, to estimate the probability of the predictor within the class, right? So you'd have to estimate those 10 bar heights, right? So you'd estimate 10 parameters. Now that's not too bad. If you've got, say, 100 data points, no worries, right? You've got 10 data points per bin, roughly, and so you'll get a reasonable estimate. If you've got 1,000 data points, you'd have 100 data points per parameter to estimate. You'll do really well. But what if you go to 2 dimensions? So what if we're estimating a histogram in 2 dimensions? So say we're going to use 10 bins again per dimension. Then all up, we're going to have 10 bins for, say, for the diagonal, say, of the banknotes, and we'd have 10 bins also for the margin. But those 10 bins for each one would then replicate, because for each of the margin bins we'd need 10 diagonal bins, and for each of the diagonal bins we'd need 10 margin bins. So all up we'd have 10 times 10, or 100 bins, right? Because essentially what we'd be doing is we'd be estimating the density within each pixel of a 10 by 10 grid, right? So you can think of your plot of margin and diagonal, and you would basically grid it, and you'd produce like a heat mappy type thing, right? Where you'd get your number of observations in each grid, essentially, is what you're doing. So you'd need to estimate 100 things. So if you only have 100 data points, then on average you've only got 1 data point per thing to estimate, and so your estimate's going to be really bad. If you've got 1,000 data points, then again you've still got to estimate 100 different things. You've only got 10 data points per thing, right? So in order to do a two-dimensional histogram, you need basically the number of bins times the amount of data than you would for a single dimension. The same thing extends, so if we go to 3 dimensions, then we'd need 10 times 10 times 10 things to estimate. That's 1,000 things to estimate. If we've only got 1,000 data points, again, we've only got one data point per parameter to estimate, and so we're going to have really poor estimates. The same idea applies to KDE, right? So you need thousands or tens of thousands of observations to do well with KDA if the number of predictors is, say, 3. This is this idea here. I didn't know that I'd written it up on the next slide. So if we're doing histograms and we go even further to, say, 10 different parameters, then we need 10 to the 10 bins to estimate, which is 10 billion, right? So we need to estimate 10 billion probabilities to fully specify a histogram when we have 10 variables. And even if you have millions of data points, right, you've got 10 billion bins, most of them are going to be empty, right? Because you've just got to shred those millions of observations across billions of bins. And so it's extremely hard to estimate the probability. And even if you go really, really coarse with your histogram, so you only have 2 intervals, 2 bins for each variable, you still need 1,000 bins. So you've still got 1,000 bins, 2 to the 10, right? So 10 variables, 2 bins each. And the histogram is going to be extremely crude, right? And so if you've got millions of observations, you can estimate these things really well, but your estimate is going to be really poor. So that's the curse of dimensionality. And it also applies when we have categorical data, the same idea, right? So suppose we have factor variables. We have 10 factors, so 10 grouping variables, each that have 10 groups to them, so 10 levels. Then again, there's 10 to the 10 possible combinations of those levels for each observation. And so unless we've got more than 10 billion training rows, we're only going to observe a small fraction of those probabilities. And so we're going to give a very poor estimate, right? So our estimates of those F1, F2, and so on are going to be really bad. And even if your factors don't have many levels, so say they've only got 4 levels each and we've got 10 of them, we still have about 1,000 combinations, 1 million combinations rather. Okay, so if we're wanting to estimate those distributions well, we either need a model for these things so that we can reduce the number of parameters we use, such as in the LDA case, right? In the LDA case, if we had 10 numeric predictors, all we have to estimate is the 10 means and the joint covariance, right? So we've actually only got 10 means plus the covariance to estimate, which is a small number of things. So LDA is going to be able to actually get an estimate. Now, whether the assumptions of LDA holds is a different story, right? KDA cannot possibly get an estimate in that case, right? So it's too flexible. So we need something in between, right? And so that's where naive Bayes comes in. And naive Bayes makes an extremely naive and extremely strong assumption. And the strong assumption that it makes is that all the predictive variables that we have observed are statistically independent within each class. Okay, so that means that the joint distribution of the diagonal and margin, for example, can be factored into the distribution of the diagonals times the distribution of the margins. Okay, so it's assuming that there's no correlation present between the margin and the diagonal. And actually, for the Swiss banknote data, that's actually a pretty sensible thing to do, I think. So this is what the distribution looks like. So within the blue class, there doesn't seem to be a lot of correlation there, does there? Within the red class, maybe there's some correlation. So there's an increasing trend between margin and diagonal, but it's not super strong. And so making the assumption that these two things are independent is probably going to work quite well. Okay, and in terms of the maths, what happens is that the FJs is the joint distribution of all of the predictors given the class. Then we can factor that into the marginal distribution of each variable of each predictor given the class, and then just product them all up, multiply them all together. Okay, and so the idea is that each of these things individually is easy to estimate because we're going to have a reasonable amount of data, right? So if you're within the you only need to do a histogram for the first variable, multiply it by the histogram for the second variable, and so on. So each of these histograms or each of these kernel densities is easy to estimate in terms of you've got enough data to get a good estimate of the shape of it. And then you just multiply them all together to get the joint distribution. So the massive decrease in the number of parameters you need is due to the super strong assumption of independence. Okay. So if p equals 10 and we want to estimate histograms, then to estimate each of the components, we only need to estimate 10 bins. Okay, and so we only need to estimate 10 times 10, right? So we've got 10 predictors, and for each one we only need 10 bins, so we only have 100 probabilities to estimate the whole thing. And so we should be able to get pretty good estimates of those 100 probabilities with, say, 1,000 data points or 10,000 data points. Okay, and the same argument applies to categorical features and to kernel density estimation. So the independence assumption is extremely strong. Now, it's also almost certainly wrong, right? In some cases, will be extremely wrong. Okay, so there's a trade-off here, all right? And so naive Bayes is basically saying, well, the independence assumption is almost certainly wrong, so I'm going to trade off a bunch of, so I'm going to be biased, right? But I have way fewer parameters to estimate, so I'm going to be reducing the variance, right? So it's that bias variance trade-off coming into it again. Okay, and this is an explanation of that idea of the bias variance trade-off. So how do we do it in R? Well, there's the naive Bayes engine function from the in Parsnip, as per usual in tidy models. So all we do is change the model type again. So what the naive Bayes function does is it actually uses kernel density estimates for all of the numeric features. You can change that, so you can use normal distributions if you like. So for example, if you've plotted the data and it looks as though normal distributions are going to work, then perhaps using them might be a good idea. It's not actually too bad to use KDEs because they're only one-dimensional KDEs, so as long as you've got kind of 100 data points, you're going to estimate them really well anyway. That's in each class. You're going to estimate them really well anyway, so there's not really any benefit for switching to an even smaller number of parameters to estimate using a normal distribution. And then, of course, everything else is the same because that's what tidy models does, right? So let's have a look and see how well we do for the jam donuts case. Now, the jam donuts case, there's clear correlation, right? So let's go back and have a look at the actual data without that. Do we have the actual data here? Here we go. So there's probably no correlation within the jam class, right? There doesn't look to be a trend in there, but there is a trend in the donut class, right? If x1 is large, then x2 is constrained to be between about -2.5 and 2.5. Whereas x1 is small, then x2 is constrained to be between, say, 1 and 5 or -1 and -5. So there's correlation there, right? It's not the traditional sense of linear correlation, but there's correlation. So the assumption of independence is definitely not true. But let's see how well it does anyway. So we're going to be introducing bias because we know it's not true, but the advantage is we can estimate these things really easily. So there may be an advantage in the reduction of variance. So again, we're just using the naive Bayes engine. Okay, we're fitting our class in terms of the two predictors x1 and x2 in the same way as we did before. Using augment, everything else is the same, and you can see that on the training data, we are getting all of the donuts correct and almost all of the jam correct. So we're doing extremely well, even though there's the independence assumption is wrong. The way it's wrong is not too bad. So here I've plotted the two-dimensional KDE, which is the product of the two one-dimensional ones, which the naive Bayes is actually doing. So what naive Bayes is doing is it's estimating the one-dimensional KDE within the jam for x1 and the one-dimensional KDE for the jam for x2, and it's multiplying them together to give this distribution for x1 and x2. And it's doing the same thing for the donut. So the KDE distribution for x1 is this bimodal distribution, and the KDE distribution for x2 is again a bimodal. And when you multiply those two together, you get this quadmodal type situation, right? So you get that peak times this one, which is this one here, that peak times this one, which is this one here, and so on, right? But the idea is that kind of squarish look that you have does a pretty good job of saying that actually as long as you're sort of in a circle of diameter roughly 3, you're probably a donut. So while the independence assumption is wrong, it's not so badly wrong that making that assumption is going to result in a really poor estimate. Okay, so we end up doing reasonably well. If we don't use kernel density estimates, however, we're not going to do as well, but it turns out it's actually not too bad. So if we specify use kernel equals false, then the distribution in the jam is going to be the same because it's roughly normal anyway, right? So that looks roughly the same. But the distribution of the donut, right, we don't have two peaks, we've only got a single peak. And so when you multiply them together, you get this very diffuse normal distribution. Now this is going to still work because the vast majority of the observations in the jam, that peak in the jam is just so much higher that essentially your decision boundary is going to be a circle around here, right? And so as long as you're in the middle, you're jam, and if you're not, you're donut. Okay, so while this is a really poor estimate of the distribution in the donut, it's good enough because of the way the two classes are structured. Okay, so all of the jam points are in the area of highest density for the donut group, right? So here's the area of highest density for the donut group, and there's no donut observations there at all. But because the distribution of the jam density is still even higher there, we still do really well. Okay, so you can see that we're getting the donut perfect and we're getting most of the jam correct. Okay, so even though the assumption of independence is extremely poor here, because of the way the two classes are constructed, because of where they are essentially, even the extreme assumption of independence and normality still does really well because the variance is different between the two groups, right? So essentially this is picking up the fact that the variance of the donut group is way more than the variance of the jam group. So this does better than LDA because while the assumptions are really similar, right? LDA makes the assumption of normality but constant variance. This makes the assumption of normality but allowing the variance to differ between the groups. Because the variance differs between the groups and the means don't, this does well, whereas LDA does extremely poorly. Okay, so the assumptions underlying the model are what's important for telling whether a model is going to do well or not. And in some simple cases like this, where you just have 2 or 3 variables, you can often just plot them in order to, and then be able to tell, based on the assumptions, which model is going to do well and which model is going to do poorly. In practice, with many variables, that's hard to do. So in practice, with a bunch of variables, you often start by doing some plots just to see if there's anything really jumping out at you. And then you may as well just go and fit all the models that there are and just see which one does well. Because we know that even though the assumptions are broken, depending on how they're broken, may or may not affect the result. Okay. Next week we'll start looking at discriminant classifiers, which estimate the probability of the class given the predictors directly, rather than generating them with the probability of the features given the class like we have here.